So in this video, we're going to look at problem 5.47 from the homework. We're given a beam and we're told to neglect its thickness. And we notice that there are two forces actually loading this beam. Force F acts purely in the downward direction. We're told that it has a magnitude of 55 kilonewtons. This 26 kilonewton force has both a downward component and a component that would actually push the beam to the left. So if this weren't supported by any support structures, this beam would naturally tend to translate down and to the left. So what's actually keeping it stationary? Well, what's keeping it stationary are the so-called reactions that are being applied at the actual points of support. At point A, we have a pin connection, and at point B, we have a cable that's attached from B to C. Now, what do we know about the nature of the reactions that are actually being supplied by the pin connection at A and the cable connection at B? Well, remember with the pin connection, if you actually pin something, that pin is capable to overcome the tendency of the beam to translate in the horizontal direction. It's also able to keep it stationary in the vertical direction. However, the beam could still rotate freely about that pin connection. So at point A, there are two kind of components of the unknown reactions. A horizontal component that corresponds to its ability to basically stop this force from pushing the beam to the left, and a vertical component that kind of is going to team up with the tension supplied by this cable to keep it going down. In addition, of course, remember that the cable is going to exert a tension on this actual beam that's going to be directed along the actual cable itself. So when we talk about the reaction associated with this cable, it only has one unknown because it's only the magnitude of the force that is unknown. And of course, that is the tension in the cable, and it's directed along the cable. So three unknowns, AX, AY, and the magnitude of the tension of the cable. And for an actual 2D coplanar force system, as long as we're treating it as a rigid body and not a particle, which we have to since these forces aren't concurrent, we can write three equations of equilibrium. So we have what's known as a statically determinate situation, where the number of unknowns equals the number of equations that we can write. So for actually solving for the unknowns associated with the reactions, the first thing that we need to do is to draw a free body diagram. And when I draw this free body diagram, I'm just going to draw it and represent the beam as a single line. Because remember that we're effectively neglecting the thickness, so that's kind of the model that we're taking on. Here at point A, I will replace the pin. If you remember, when you draw a free body diagram and you separate the beam from its actual support structures, you want to replace the effect of the support structure by what it is actually doing to keep it stationary. So remember that this pin has the capability to push the beam up and push it to the right. Now, of course, we don't necessarily know, we kind of can through physical intuition, that what this pin is doing is pushing up and not pulling down, or pushing to the right and not pulling to the left. But if we just always assume that the reactions of pin connections have a vertical component that goes up and a horizontal component that goes to the right, if it turns out that under a particular loading condition, those aren't the actual directions of the reaction, then these numbers will just turn out to be negative. So in general, when you are drawing free body diagrams and replacing support structures by reactions, it's good to always assume that the reactions go in the same way and let the math work itself out. So that is the reaction at A associated with the pin. In addition, 2 meters away, and I'll try to draw this relatively to scale, we have the 26 kilonewton force applied. And that geometric information is going to allow us to decompose it into components, which we'll do soon. Let me just copy that over. We got a 12, 5, 13 triangle, and that tells us that of this magnitude, 12 thirteenths corresponds to the y component, and 5 thirteenths corresponds to the x component. In addition, 4 meters from that, all the way at the end of the cable, or I should say the beam, sorry, I had the cable on my mind, we have the downward force F, and it has a magnitude of 55 kilonewtons. And then we have the actual tension associated with the cable pulling up along the direction of the cable, and that is a quantity that we need to find. So we have three unknowns and three equations. So we're in good shape. We have what's known as a statically determinate system. So remember that technically there's an infinite amount of combinations of three equilibrium equations that you can write. However, you typically choose your rotational equilibrium equations, at least one of them, in order to isolate one of the actual unknown reactions. Now, what do I mean by that? Well, if we think about actually enforcing rotational equilibrium about point A, what that means is that the sum of the moments of each of these forces about point A has to be zero. A nice a reason to do that is that these reactions at A, AX and AY, they won't contribute a moment about point A because their lines of actions pass directly through this point. In addition, if we think about this 26 kilonewton force as having a y and an x component, the x component also won't contribute to any rotation about point A because its x component will also go right through point A. Same thing with the x component of TBC. So if we sum all moments about point A as our initial equilibrium condition, what that's going to allow us to do is to solve for magnitude of TBC directly because the y component of TBC will contribute a rotation about point A. And in addition, it's going to be a relatively simple equation because many of these forces have a line of action that goes directly through point A. So note that here, AX, AY, the 26 kilonewton force, I'll just call it 26. I'll say its X component, along with TBCX. It would help to actually write that correctly. TBCX won't contribute here. And the reason they won't contribute is their line of actions go actually through point A. So when we sum all moments about point A, doesn't contribute. Let's talk about the y component of the 26 kilonewton force. So what I'm going to do is actually first decompose that into its y component. Remember that based upon this information that we're given geometrically, the y component is 12/13 of the magnitude. So I'll write that in here. And that is actually the force. And when we do the scalar formulation of a moment about point A, what we need to do next is determine the direction of rotation, pin it at A, and pull down in the y direction. Notice that that is a clockwise rotation. So that's going to be negative. And then determine what the perpendicular distance is. So the line of action of the y component is purely vertical. So that perpendicular distance is 2 meters. So that is the direction or the sense because it's inducing a clockwise rotation. That is the magnitude of the y component, and that is the perpendicular distance. Next thing we want to do is the 55 kilonewton force. Hopefully everyone sees that it will also induce a clockwise rotation. So by our sign convention, it is negative. It doesn't need to be decomposed because it's purely in the minus y direction. And the perpendicular distance here will be 6 meters. If you think about it, the tendency of both of the vertical components of both of those applied forces to rotate the beam in the clockwise direction is counterbalanced by the tendency of the y component of the tension to rotate it back in the counterclockwise direction. So the y component of the tension, if you think about it going up and pin at A, it's going to be a counterclockwise rotation, so that'll be positive. And we need to decompose TBC into its y component, so that'll just be TBC. And using the same geometric technique that we did to decompose the 26 kilonewton force, the y component will simply be 3/5. And then the perpendicular distance in this case will also be 6. And that whole thing is going to be equal to 0. So that will allow us to solve for TBC directly. So we'll say TBC is just going to be equal to, and I'll let you actually finish that part up for your homework. But you know this is just a number, this is just a number, and that is just a number, and from there you should be able to solve. So the next thing that you need to do is to just simply solve for the reactions AX and AY. And to solve for the reactions at AX, we'll sum all the forces in the X direction. We'll say that has to be equal to 0. Counterclockwise, positive. What's going on here in terms of the forces acting in the X direction? Well, we have AX going to the right. Then we have the Y component of this 26 kilonewton force going back to the left. So since it's pushing to the left, I'll use a minus sign. The Y component is 5/13 of that 26 kilonewtons. Of course, the 55 kilonewtons doesn't have an X component. It's purely in the Y direction. I think I was saying Y there. I'm sorry, I meant the X component. If you notice, the X component will push to the left. It will be 5/13. And for TBC, notice that since this cable's always had to be in tension, it is pulling the beam to the right. So that will have a positive sign associated with it. And then we just need to decompose TBC into its X component. Given the geometrical information that we have, its X component will be 4/5 of whatever that magnitude is. So just going back and making sure we got everything, the pin reaction at A has an X component. We've included that. The 26 kilonewton force exerts an X component to the left. We've included that minus. And TBC exerts an X component to the right. We've included that, and then we decomposed it correctly. So these all have to add to 0. And if you basically substitute in your value of TBC, you'll be able to solve for AX as well. And basically what this says is, so TBC from a kind of engineering intuition point of view, has to be the reaction that counterbalances the tendency of these two vertical components of the forces to rotate in the clockwise direction. So TBC is kind of determined by how much it takes to keep this thing from rotating about the pin. Once you determine that, then what this equation is saying is that AX basically is going to counterbalance whatever the remaining portion of that 26 kilonewton force, its X component wasn't picked up by the cable. So this is how much actual the cable is picking up to pull it back to the right. 26 kilonewton force has a component pushing it to the left. The X component of A is just going to take care of whatever this the X component of the tension didn't take care of. So that's how you get AX. So I'll say that we can solve for AX from there. We can solve for TBC from here. And of course, we can also sum all forces in the Y direction and set it equal to 0. What do we have here? Well, we have our last remaining unknown, AY, which we're assuming goes in the actual positive direction. We have the Y component of the minus of the 26 kilonewton force. And of course, that is minus since it's actually pushing in the downward direction. We already said that the Y component is 12/13 of that magnitude. We have the minus 55 kilonewton force going in the downward direction. It doesn't need to be decomposed, as we already said when we computed the moment about A. And then we have the Y component of the tension, TBC, and its Y component is 3/5. And if you think about it, did we get everything? We got that Y, we got that Y, we got that Y. So 4 terms here. Yep. And you know this from equation 1. And that should allow you to solve for this directly. So that's the way that you actually go about setting that problem up. Hopefully it made sense. If not, just feel free to reach out. I'm sure the majority of you, now that you've gotten to this point of the course, could have did that problem without a hint. But just in case you wanted to see one more example and kind of think about intuitively from a physical perspective what's going on. And I didn't say what's going on for the Y component of the pin, but it's the same thing. This tension value has to be determined to stop the beam from rotating in the clockwise direction. So whatever that needs to be, basically the Y component at the pin will pick up the remainder of that downward force associated with the two applied loads. So I will see you all in the next video.